Imagine that you and I are on a mission to fall into a black hole.
It's a bit nasty around these things. You cease to stay together.
We're one long string of atoms? Well, what are we?
Yeah, and then the atoms get separated.
If a black hole will one day end up as nothing, the normal vacuum of space, what happened to you and me? What happened to all of that stuff?
I mean, this is the central question. The laws of nature are quite clear on this. So that's what bothered everybody for a very long time.
What happened? What's the end of the story?
So what happens?
I'm so excited about this. The video you're about to watch is a deep dive into the cutting-edge research happening right now about black holes. It's awesome. It's the extended cut of an interview that I did with famous physicist Dr. Brian Cox for a shorter Huge If True episode all about what would actually happen if you fell into a black hole. That episode is incredible, and I've linked to it in the description. But there was so much weird and mind-bending stuff in this conversation that didn't fit into that shorter episode, and I knew that you'd want to see it. So we decided to release the full extended cut. It's just too cool, and I think you'll love it. So strap in, because the cutting edge of black holes is wild.
We're good.
Great. Would you mind just starting us out by introducing yourself however you like?
Yeah, so I'm Brian Cox, and if you want the title, the full title, I'm Professor of Particle Physics at the University of Manchester, Royal Society Professor for Public Engagement in Science, and Visiting Scholar at the Crick Institute in London.
And how do you describe what you do every day?
What I do every day? Physics. And that's kind of the way that I see myself. If someone asks me what I do, I say, I'm a physicist. But actually, of course, most of my time now is spent on the public engagement side. And I kind of fell into that accidentally. But I still, maybe it's a thing, maybe there's some deep psychological thing going on. But I never say TV presenter or whatever it is. I just say physicist.
Mm-hmm. Well, that's what I want to talk to you all about today. So imagine that you and I are on a mission to fall into a black hole. And we have some imaginary spaceship that can take us as far and as fast as we want. So we get up, we walk outside, we get into our spaceship. What now? What is a black hole, and how do we find them?
So a black hole, it's interesting that the idea, or the first glimpse of them theoretically, came very shortly after Einstein's theory of gravity was published in 1915, although it wasn't recognized as such at the time, this glimpse. But essentially, what does Einstein's theory do? It's important for what follows. It's a theory of space and time, and how space-time, which is often described as the fabric of the universe, responds, or warps or curves, to matter and energy in the universe. So the equations, basically the theory that Einstein published all those years ago, will say, give me some distribution of matter, something like a ball of matter, and the equations will tell you how the fabric of the universe is distorted. And by the way, the force of gravity in that theory then is the response of everything else in the universe to that distortion. So Einstein would say, what are we feeling now? Newton would say it's a force between us and the Earth, right? But Einstein would say there isn't a force. What we're responding to the distortion in the fabric of the universe created by the Earth. So that's John Wheeler, actually, the great physicist, put it beautifully. He said, matter tells space-time how to curve, and space-time tells matter how to move. And that's it, right? So that's Einstein's theory. So in 1916, shortly after it was published, a man called Karl Schwarzschild remarkably managed to solve the equations for a perfectly spherical, non-spinning ball of matter. It's the simplest thing you could do, which tells you how space and time are distorted by it. And that's a model for a star. It's the simplest thing you could do. So he solved the equations. It's a remarkable thing. In those equations, there is a description of a black hole, although it wasn't realized at the time. So it's a remarkable simple piece of mathematics, actually. So essentially, what's the idea behind a black hole? One way to think about it is that could you remove the star from this fabric, but leave the distortion behind? So if you do that, you get the description of a black hole. But you might say, what do you mean? How can that be formed in nature? So you think about what a star is. Then a star is a balancing act. So it's a mainly hydrogen and helium collapsing under its own gravity. That's how our sun formed 4.5 billion years ago. So it's collapsing. So what stops it collapsing? Well, as it collapses, the core heats up, and that initiates nuclear fusion reactions in the core. In the case of our sun, it's hydrogen being fused into helium. That releases energy, which creates a pressure which holds the thing up. So it's balancing it, but it needs the fuel. And it's not infinitely big, of course. So at some point it runs out of nuclear fuel, and ultimately no more fusion reactions can occur in any star. And so the star will resume its collapse. So the question is, well, is there something that stops it? Because if there isn't something that stops the collapse, then it will collapse without limit. and so actually, if you look at the history of physics in the 20s and 30s, people were saying, well, we'd like to avoid this idea that the thing will collapse without limit, because if it does, then Schwarzschild's equation predicts some very strange things indeed. And so people kind of try to avoid it. It was really actually Oppenheimer and his student Schneider in the late 30s, just before the Second World War, that showed that really, with some assumptions, it looks like a massive enough star could actually collapse without limit. So what does that mean? Collapses without limit. It means that essentially it does what I said. You essentially remove the star from the fabric of the universe, leaving the distortion behind. And the black hole, the idea behind the black hole is, let's say you take the sun, a star the mass of the sun, and you just collapse it, and you keep on collapsing it. You get to a point when the radius of the sun is not 700,000 kilometers, which is what it is in miles, 500,000 miles. I'm going to use kilometers because I can't remember the things in miles.
Our audience will appreciate that.
Everyone can convert it afterwards, right? So 700,000 kilometers. And you squash it down, and you squash it and squash it until its radius becomes 3 kilometers. 3. Then there are several ways to look at this. One is that on the surface, the speed you'd have to travel to escape its gravitational pull, it's called the escape velocity, would exceed the speed of light. That's one way to think about it. So even light rays emitted from the surface, if you could squash it down that far, would just stay there. They would not escape because they'd be trying to go at the speed of light, and the escape velocity is the speed of light, and they just stop. So what happens then if a star collapses inside that number, which for the mass of the sun, 3 kilometers, is called the Schwarzschild radius, then it will collapse without limit. Nothing will stop it. And so all you will get is essentially the geometry of space and time, the curvature. And that's a black hole. So it's a thing that traps light in that sense. So you think about that. If you have this surface, and space and time are so distorted there, that if you go in across that surface, it's called the event horizon of the black hole, then you can't get out. One way to think about it is you'd have to travel faster than light to get out. Another way to think about it is that there's a beautiful model, which is my favorite model. It's called the river model of a black hole. You can write the equations as the space being like a river that flows into this thing, almost like a sinkhole or something in space. And the river of space flows at the speed of light inwards on the horizon, and then faster than light inside. So if you imagine that you're a photon, a particle of light, you're like a little fish swimming against the tide. But if the tide's going at the speed, as fast as you can swim, the speed of light, you can't get out. Not only can you not get out, but you're going inwards towards something. And this thing, the something, is called the singularity. You say, what is this thing, the singularity? And I think it's really tempting to picture it as some infinitely dense point to which this star collapsed. When you draw a map of space and time, what you see really clearly is that this singularity thing is not a place in space, it's a moment in time. And it's in fact the end of time in Einstein's theory. So a way that I often kind of picture it or explain it to myself is that space and time have become so distorted that when you look at it from the outside, they flip roles. So space has become time, and time has become space. In the mathematics, if you put a little graphic up, you'll see that the plus and minus signs in the Schwarzschild equation reverse, right? And so they flip round, and so they change. So what you thought of as an infinitely end place in space to which the star collapsed has become a moment in time. And a way to think about why you have to go to it then, it's really beautiful because you think it becomes something that's in the future for anyone or anything that crosses the horizon. Mm. It's in the future. So it's like if you say, well, I want to escape this thing, it's like saying, I want to escape tomorrow. If I said to you, let's run away from tomorrow, you go, I can't run away from tomorrow. It's in the future. That's what this thing behaves like, the singularity. So that's the Einsteinian description of a black hole.
I want to take that step by step so that I
there's
can
a lot of it in there,
begin
but it's
to
fun.
understand it. Okay, so in order to understand this,
cool.
Let's imagine that we choose the black hole at the center of our own galaxy.
Yeah.
Sagittarius A star, I think it's called.
Yeah.
I know that we took this picture of it in 2022.
That is by the Event Horizon Telescope, Sagittarius A star.
What are we looking at here?
So here, the light, you might say, what is the light in this picture? So it's not from the black hole, because we've just said black holes trap light. It's from what's called the accretion disk around the black hole. So you're to imagine really material spiraling around in orbit around this very dense object and very violently orbiting. And so it heats up and it emits light. Imagine a flat, thin disk of material around the black hole. But this does not look like that. What you're seeing is the distortion, the curvature of the light rays. Because we said that you might think, well, light travels in straight lines. But Einstein's theory says that in the vicinity of this thing, the fabric of the universe itself is distorted. So the light, the paths of the light rays follow the distortion.
So that's like why in an animation it looks like it's going over the top and around the sides at the same time?
So what you're seeing, this famous image of a black hole, like if you think of the film Interstellar, that code, by the way, is an implementation of Einstein's equations. Kip Thorne and others helped them do that. So it's really a prediction. So what you're seeing, so imagine this disk of material around this thing, like picture in your mind's eye Saturn. Mm-hmm. Then light rays, let's say from your perspective, from behind the black hole, on the, let's say on the disk, mm-hmm. go around into your eyes. Sometimes they orbit and then go around into your eyes. And they go into your eyes from every point on the disk, from underneath and at the top and behind. So you have light rays going always around this thing. So you see that. That's what you see as an image. So there's a prediction of Einstein's theory, which is a real black hole should look like that. It's the characteristic donut shape mm-hmm. that you see. Well, here's an image with radio telescopes of such a thing, and it looks like the prediction. It is a bit blurry, but this is at the center of the galaxy. Very difficult. This was actually the second one that was imaged. The first one was in a galaxy called M87, mm-hmm. which is 55 million light years away and is bigger than this one. Bigger, which I mean, so this one's about 6 million times the mass of the sun, give or take. The one in M87, 6 billion times the mass of the sun. So this is the baby supermassive black hole that we've got.
So this is my next question. Our black hole, how big is it compared to other black holes that we know exist?
So it's a smallish one.
And what's the
not smallish.
Scale?
It's a supermassive black hole. But we think that I would say all galaxies. Maybe there's an exception or so, but pretty much all galaxies have supermassive black holes at their centers. We don't quite know why, actually. We don't quite know how galaxies form in the early universe. It's one of the things that the JWST, the James Webb, is looking at in some detail, the new space telescope. But to good approximation, all galaxies have these things. And they can be different masses. So, as I said, the M87 galaxy has one that's 6 billion times the mass rather than 6 million times the mass. So, but how big is it? So the number I always remember in my mind is the Schwarzschild radius of the sun, mm-hmm. which is, as we mentioned, it's the radius you'd have to squash the sun down to make a black hole. And it's 3 kilometers. So it goes like the mass, so you can work it out. So if that's 6 million times the mass of the sun, then the Schwarzschild radius is 6 million times 3 kilometers. Mm-hmm. So it's kind of easy to do the math, actually. So that would be you might call it, you have to be careful with your language, but let's let's say that this thing it gives you an idea of the size of this structure. So the disk is outside it is much bigger.
I did the math with Earth's radius.
Yeah.
And it seemed to suggest that we would become a black hole if we compressed everything on Earth and all of us into something about the size of a pea.
It's about, from memory, about 0.8 centimeters, I think. Something like that, just less than a centimeter. So you're right, about that big.
Do black holes that small exist?
No, we don't think so. So even black holes the mass of the sun, the sun will not form a black hole. When it runs out of nuclear fuel, it will collapse, and there's something that can stop it collapsing.
The force of electrons.
It's called a white dwarf star. It's beautiful calculation, by the way, that. You can do the calculation. It's great. So what stops it, as an aside, is that as electrons, there's something called a Pauli exclusion principle.
I read about this, yeah.
So electrons don't want to be close together, roughly speaking, you could say it like that. So as you squash the thing, the electrons get closer together, and so they kind of separate away from each other and go into smaller and smaller little regions of space because they're trying to stay away from each other. But there's also something called the uncertainty principle, Heisenberg's uncertainty principle. So as you confine them into smaller regions, they start jiggling around faster and faster. And ultimately you can reach a limit where they're essentially trying to jiggle at the speed of light, and they can't. And so there's a limit to how much pressure that process can exert. And it turns out it's 1.4 times the mass of the sun, which is called the Chandrasekhar limit. So you can do that calculation, but it's a beautiful calculation because you could have worked that out not knowing that stars exist. All you need to know about is quantum mechanics and relativity. And you can make the calculation, what is the biggest lump of stuff that can be held up by this jiggling of electrons? It turns out it's 1.4 times the mass of the sun. Then you look into the sky and you see there are these things called white dwarfs, these collapsed stars, which are, and there's none more massive than 1.4 times the mass of the sun. So it's very beautiful. And then you can get neutron stars, which are held up by the jiggling of neutrons. But ultimately, if you go to something that's three times the mass of the sun, something like that, a bit more, then nothing stops it collapsing. Yeah. And that's when you form a black hole. So the lightest black holes that we know of are around that mass, right? And then we know of them that are 10, 20, 30 times the mass of the sun from collapsed stars. And then these things, which are millions of times or even more the mass of the sun, which are the heart of galaxies.
So we've launched in our spaceship. We are hurtling toward this black hole.
Yep.
Could you walk us through step by step what happens from now until when we hit the event horizon?
Yeah. So the first thing to say is that it's right at the heart of Einstein's theory is something called the equivalence principle, which was the idea that really led Einstein to the theory itself of gravity. And so you don't feel its pull. What you do is you just fall freely towards it. So we're falling towards this thing now, and we turn our rocket motors off. We can't tell. If we can't look outside, we can't look out the windows. We're just in free fall. We're just floating. So it's like the astronauts on the International Space Station. We're just there. So it's fundamental to Einstein's theory. It's very important, actually, for the problems that follow that we're going to talk about, that you just freely fall towards this thing. So we could be approaching this in this room now, and we would have no clue that's what's happening. And in fact, so we're approaching the event horizon of a very big black hole like this. For a black hole of this mass, then we wouldn't even notice something, according to Einstein's theory, as we fall across the horizon into the interior of the black hole. So we'd fall across the horizon. From our perspective in this room, according to Einstein, and we'll go for that caveat a bit later, but according to Einstein, into the interior of the black hole we go, and we notice nothing.
What about when we're in the accretion disk? Wouldn't we be banged around by a lot of stuff?
So we might get in a bit of a mess as we go through the accretion disk, but we're talking about the pure gravitational thing.
Yes.
You're absolutely right. It's a bit nasty around these things. So there's stuff, but that's nothing to do with the black hole itself, right? It's nothing to do with the fundamental physics. It's all the X-rays and all this nasty gamma, all the stuff that's been irradiated from all this hot material around it. So yes, that would be a problem. But if we had let's say that our room, this spacecraft, is magically insulated from radiation
Yes.
and heat and all those things, then nothing. In we would go into the interior. The caveat,
Please.
there's a lot of caveats, but one thing I should say is that it matters that description I've given, it's for a supermassive black hole.
Yeah.
If this was a smaller black hole, so smaller, less massive, a few times the mass of the sun, then at some point you experience what's called tidal gravity, tidal forces. So those are things that raise the tides in the oceans of the Earth. The tidal forces, we will start to, in our freely falling trajectory towards the black hole, at some point you start to feel the tides. You start to get stretched and squashed. And
we feel it.
You'll feel it eventually. You'll really feel it eventually, because formally, as you get very close to the singularity, you get infinitely stretched and squashed. So you really feel it.
I want to talk about that
Spaghettification.
Inside. Yes, that's my favorite.
But so for a smaller black hole, as you approach the horizon, you'll feel those forces. But for the big ones, you don't feel the tides until you've gone into the interior.
So we're moving toward the event horizon. We're somehow insulated from the messiness of the accretion disk. We're moving toward it. I've heard that there's a moment where the physics of this are such that if you and I are actually falling in, if we look to the left and the right, we would actually see the back of our own heads.
Yeah.
Is that anywhere close to correct? And can you tell me about the other little details as we approach the event horizon that you think are important?
Well, one of the biggest details, it's not even a detail, it's one of the most shocking things about this, is I've described this, us falling into the black hole. And we're saying, in this room where we can't see out, what do we feel, what can we measure? And the answer is you can't measure anything and we don't feel anything until we get inside and we approach the singularity for this one. But from the point of view of someone outside, the description is very different. So what would they see happening to us as we fall towards this thing? So even in Einstein's theory, with nothing else, no quantum mechanics or anything, then what they would see is time tick more slowly for us.
Mm-hmm.
So they would start to see, as we approach the black hole, if they could see our watches, if we were transmitting to them or whatever it is, transmitting from these cameras, we were sending it out to them. They would see our time tick more slowly, more slowly, more slowly, and they would see our time stop on the horizon. So they would never see us fall in. So from the point of view of someone outside, nothing goes into the black hole, ever.
So what, do they see us imprinted there forever, or does the light from us slowly fade until... It
would fade because also you could picture, there are many ways of picturing it, but you could say this light is climbing away from through this gravitational field, so it's getting stretched. So we get redder and redder and redder, redshifted, infinitely redshifted. Time passes more and more slowly until it stops on the horizon when viewed from the outside. From our perspective, we look at our watches, they go at 1 second per second. Mm-hmm. And that's absolutely central. There's nothing weird. Well, there's something weird there, but there isn't according to Einstein. So it's pure Einstein's theory. So that's the first thing to say. And it's a clue to the interesting things about what we're going to talk about. What follows is that there are different perspectives on what's happening here. There's a perspective from our point of view, we're going in for a big black hole. From the point of view of someone outside, we never go in. And that's going to be kind of important for what follows. But there's nothing that's not described by Einstein's theory in that particular bit of the description.
Hang on, let me show you something else that's really cool. This is my privacy dashboard. It shows how many data brokers I've gotten myself removed from. Actually, our sponsor, Incogni, has gotten me removed from. So why does this matter? Well, data brokers make money buying and selling your information. Sometimes they sell to businesses, so maybe I get more spam. But also, with more data, these brokers can form a picture of you, a shadow profile. which they can then use in ways you might not want. But Incogni can force many of them to remove you. Let me show you. So they reach out to data brokers on my behalf and they say, hey, remove this person. And then, crucially, they follow up to make sure that I actually got removed. I really appreciate this, and I think you might too. If you want to try it out, use the code CleoAbram at the link below and get 60% off an annual plan. Now, back to black holes. So at this moment, we cross the event horizon.
Yeah.
And we don't feel that.
We could have crossed it now.
Just now.
Wouldn't notice.
And our experience now is completely inside the blackness of the black hole from an outsider's perspective.
Yeah.
Gravity is increasing faster and faster. And this is where we get to maybe my favorite word that I have learned in the process of this, which is my understanding of this is when the gravity at your feet is so different from the gravity at your head that you begin to stretch in a very dramatic way. And this is spaghettification.
Yeah.
Could you explain what is happening here?
Yeah. And
as we
you
get
said,
spaghettified.
one way of thinking about it is that another way of thinking about it is just that the distortion in space-time is not constant over the length of your body. Right? So when we're falling in, we might as well be, this is the Einstein's equivalence principle in action, we might as well be in flat space because the distortion, it's like saying on the surface of the Earth, if you look at a square mile of the surface of the Earth, you don't see the curvature, right? You have to go to bigger distances to see that you're on a curved surface. It's kind of like that. So the distortion, the difference in gravitational pull, as you said, or the distortion, you don't feel it until it becomes very distorted. Or there's a big gravitational pull when you get very close to this thing. And then you start to see that, and actually it works. It's not only stretching, it's also a squashing. So the way the tidal gravity works is to squash in one direction and pull in the other direction.
So we are getting...
So you feel it. So you start to feel this strange sort of sensation of being stretched and squashed. and as you go closer and closer to the singularity, those effects become much more extreme until they're so extreme that, first of all, you cease to stay together.
We're one long string of atoms?
Yeah,
or what are we now?
And then the atoms get separated, and then the protons, the quarks inside the protons will get separated. And ultimately, according to Einstein's theory, the tidal forces become infinite. So formally infinite. And so everything is gone. Everything's been ripped apart, and this is what we call the singularity. So the whole thing kind of gets very extreme and breaks down ultimately in Einstein's picture.
The question that when I began this story I wanted to ask you is, what is at the center of a black hole? But in doing this research, I now understand that talking about the center is also a little bit incorrect.
Yeah.
How should I actually think about what is happening at that singularity?
Well, I mean, the first thing to say is we don't know, right? So we can talk about the current research and speculation. We don't really have the tools to describe it. So a way to think about Einstein's theory is that, as I mentioned earlier, it really tells you how space and time are distorted. They also kind of get mixed, get up from the point of view of someone outside. So then you'll see that space and time are getting warped and distorted. And as I mentioned, they get so mixed up that on the horizon, you see that they flip. So the thing to bear in mind for all that follows with Einstein's theory is this very central idea that if you're freely falling through space or over space-time, if you like, then you don't, in the absence of these tidal effects, you really cannot tell that you're where you are in the universe. If you're close to a black hole, close to a big star, orbiting around a galaxy, just falling, whatever it is. So I think that's the key idea, this so-called equivalence principle. But of course, as we said before, the thing about a black hole is that why don't you see that? You could say, why don't I see these effects on the Earth? This distortion, this mixing, and you do. So you see it in GPS satellites, for example. So if you think about what I said as you go closer to this thing, then as viewed from the outside, time passes more slowly. So you could say, well, why doesn't the Earth do that? And it does. So what you see is that time ticks at a different rate, by which I mean clocks tick at a different rate, atomic clocks or biological clocks. So you age at a different rate in orbit than you do on the surface of the Earth. And you're seeing this is the same effect. The reason it gets very extreme, I should say, it's quite a big effect for even near the Earth. So the drift is tens of thousands of nanoseconds per day. Time, a difference in the rate that time passes at the orbit of a GPS satellite and on the ground.
And we have to accommodate for that
you have to
when
accommodate
we
for
deal
that,
with
otherwise
GPS.
it doesn't work.
Yeah.
There's tens of thousands of nanoseconds per day, even around the Earth. So the question of black hole really is, as you said before, if I could keep the mass of the Earth the same, but shrink it down to the size of a pea, then how does that distortion change as I go closer and closer to this immensely massive pea thing? Then how does this is the effect that time keeps going more and more slowly from the perspective of someone outside until you see it stop on the horizon, which is, we said for the Earth is around a centimeter, just a little bit less. So it's kind of not, in some ways, this behavior of time is not unique to a black hole. It's just that in the black hole, it becomes extreme because the thing has completely collapsed.
So we have passed through the event horizon. We have been spaghettified. We have hit the end of time.
Yeah.
This is a question I think I know the answer to, but I think it leads us into our next section. Yeah. The question is, can we ever get back out?
So the answer is, according to Einstein's theory, no, because you've gone to the end of time, right? And there's no way. Basically, Einstein would say it's all over. You've got ripped to bits. Everything has got ripped to bits. You've gone to this infinitely distorted space and time, and it's just done.
What would Stephen Hawking say?
Well, Stephen Hawking initially would have said in the 1970s. What did Stephen Hawking discover in the 1970s? So in his words, he discovered that black holes ain't so black. So we've said nothing comes out of a black hole. Everything that goes in goes to the singularity, it's gone forever because the black hole lives forever. Now, Stephen Hawking calculated that if you do some essentially quantum mechanics, right? So around the horizon of the black hole, so you think about what happens. What does a black hole do? A way of thinking about this is that in quantum mechanics, which means in reality, in nature, empty space isn't empty. It has a rich structure. So the vacuum of space has a structure. And the black hole, you might say, well, this strange behavior of space and time, it must do something. And it does. It disrupts that structure. And the result is that particle photons, essentially, but what's called Hawking radiation, is emitted from the black hole. So the result, and there are different ways of thinking about what's happening. There's the very precise way. Stephen Hawking gave an analogy in his paper, and he said it's just an analogy, and people get very worked up online when you talk about his analogy, but Stephen did write it down, right? So a way to picture the quantum vacuum is that you can imagine particles coming in and out of existence all the time in the vacuum. So in accord with the uncertainty principle, they come in and out like that. You can kind of picture it like that. I emphasize it's not supposed to be a technical description, but you can picture. So you can picture these in the vicinity of the horizon. You can picture that this structure gets disrupted. You could have the situation where one of these particles is on the inside and one is on the outside. And then we know what's happening to the one on the inside. It's going to the singularity because we said the river of space is going fast in there or whatever, whichever way you want to think about it. So the other one is basically made real and escapes. So that's a picture that Stephen himself gave. But the upshot is very accurate. The point is that this particle has been shaken out of the vacuum, and it's now a real particle when viewed from the outside, and it goes away. So that what is that? What particle's been emitted? It's a temperature. It's glowing. And so that means it's losing energy, and so that means it has a lifetime. So over time, And these are enormous times, far greater than the current age of the universe for any black hole that we know of in the universe, because we don't know of tiny ones. So all the ones we know of, the immense lifetimes, in excess of 10 to the power 100 years for these supermassive ones, right? Ridiculous times. But ultimately, they have a lifetime. And that means one day it will be gone and space will be all nice and normal again, right? All you will have left will be the Hawking radiation that's been emitted over these eons of time.
Okay, I think something is missing from my understanding of the universe.
Yeah. I agree with you. Something's missing in my understanding as well, and everybody else's.
Here's what I think is missing from mine right now.
Yeah.
So all of this matter has, including us, passed through the event horizon, ended up at the singularity. It is something in there.
Yeah.
At the end of time.
So, well, yeah, and it would increase the mass of the black hole, and the black hole would grow.
Right.
Because you've gone in.
And also, I think that I know that every law that we have about the universe says that information is conserved.
Yeah.
If a black hole will one day end up as nothing, the normal vacuum of space, what happened to you and me? What happened to all of that stuff?
I mean, this is the central question. So Stephen's initial calculation, 1974, was that this radiation, the Hawking radiation, is informationless. It's information-free. So it's not gone away. It's not disappeared, the black hole. It's turned into the radiation, right? But his calculation said there's no information in that. It's what's called thermal, purely thermal. Not surprising if you think about it, because it's been kind of shaken out of the vacuum of space. So it's certainly, you would think, got nothing to do with the stuff that falls in. This is something to do with the horizon. It's not anything to do with the singularity, this stuff. So out it comes, and the calculation is very clear. So that would suggest, as you said, that the information, any record of anything that fell in, will have been erased. The energy will be the same, right? The energy is conserved. The black hole hasn't vanished, it's turned into radiation, but the radiation contains no trace of anything that fell in. That is weird, as you said, because if you think, let's imagine, you might say, well, what's the difference? What if I get this piece of paper and set fire to it? It goes, and there's just stuff, ashes and radiation. Yes, but in principle, then if you could just measure everything, which you can't, but if you could, then you could reconstruct the information on the page. Right. And you can see why, because it's got something. What's happening when you burn it is chemical reactions and there's oxidation, whatever it is, but you can trace everything back. So you can say all the atoms and things are still around, and there it is. In a black hole, you can't. So it wasn't surprising. What was surprising is that it appears there is a calculation that tells you that black holes erase everything. And as you said, the laws of nature are quite clear on this. Information does not get destroyed in the universe. It gets scrambled so you can never reconstruct it, but it doesn't get destroyed. So that's what bothered everybody for a very long time.
What happened? What's the end of the story?
So what happens?
Answer the question?
So the end of the story, we're not at the end of the story yet, but in 2019, a series of papers were published. One of the papers was by Jeff Pennington, and the other one was by another group of authors. But those papers suggest that Stephen missed a bit in his calculation. Very subtle. He could have never seen it. Yeah, I mean, that's why it took 50 years, right, to see what he'd missed. But it turns out that the radiation is not information free. At the end of the process, then all the information about everything that fell in is imprinted in the radiation, as you would normally expect. But then it becomes interesting, because you say, well, okay, so there's a calculation, this mathematics that was done. But you say, well, what's the picture then? What happened? Because I understand if I take this and throw it into the black hole, it's gone across the horizon, it's gone to the singularity. It's definitely true that nothing comes out of the black hole. But so how is this information about this thing getting imprinted in the radiation. And it turns out that it's not just, so initially quite a few people thought, well, it must be just right at the end when it's all quantum gravity and all this stuff. So the thing's just about to disappear back into the universe. And it's getting hotter and hotter, by the way, as it gets smaller and smaller. So there's more and more, it's getting more and more violent, and something weird happens and everything comes out. But it was known for a long time, it was worked by a great physicist called Don Page, that the problem about this, about the information and the structure of space, these problems occur about halfway through the black hole's life. So it's called the Page time. So the problems with the information structure of this thing occur way before you should be thinking about quantum gravity and a load of weird stuff. So there was a big challenge to physics. It's like, we should be able to calculate stuff when the black hole is halfway through its life. There's nothing weird at the horizon, but yet something weird appears to be happening. The picture of the thing is breaking down. And so then we could skip, if you want, to what is the picture of this? And I should emphasize the health warning here. This is ongoing research, and there is no agreed upon picture. And there's some other subtleties we'll talk about in a minute. But a picture of what's happening is related to something called the holographic principle at some level, we think. And another discovery that was made in the 70s, which is quite interesting, by quite, I'm using it in the American sense, it's very interesting, is that, so Jacob Bekenstein, one of the pioneers along with Stephen Hawking, calculated what's called the entropy of a black hole. So this thing has a temperature. Stephen calculated the temperature. That is inscribed on his gravestone in Westminster Abbey, his equation for the temperature of a black hole. So it's a huge fundamental discovery. Temperature is now, we understand it now. We didn't, when we first introduced the concept, we didn't know about atoms and molecules. Yeah. Then we did. And we realized that temperature is about how fast the component parts jiggle around of a thing, right? So in this water here, you heat it up, the molecules are jiggling around faster. That's what temperature is. This thing, a black hole, think about what this is. I said the description of it is just space and time. That's all it is. It's geometry. So immediately we've got the temperature of a geometry, not a temperature of a thing made of stuff, but just a temperature of space, right? So that's kind of interesting. And then Bekenstein calculates that this thing has an entropy, which implies that it hides information from us. There's a structure, there's information in there. The entropy turns out to be equal to the surface area of the event horizon in what's called square Planck lengths. So this is a remarkable idea, that you can think of the horizon. And I said, remember, it's not really there from our perspective. I said we could be falling through it and I wouldn't notice anything. According to Einstein, in we go. But then you look at it from the outside and it looks like there's information encoded on the horizon in pixels that are 1 Planck length in size. So what does that mean? Information's encoded in space somehow on the surface? And also, by the way, it's weird, isn't it? If I said how much information is contained in this room, you would say, well, it's to do with the volume of the room, right? It's for the library. It's how many books can I fit in the library? This is saying, no, at a fundamental level, the amount of information in this room is determined by the surface area of the room, not the volume. So it's almost as if nature has said you can paper the outside of the library with the pages of the book, but it's almost like there is no interior to this thing. So you start to get these hints that there's something very strange going on. What is happening here? So we've got this picture now, which was in the 1970s, of this thing that has a temperature and an entropy, which are calculated. And so that kind of is suggestive of substructure, but structure of space and time. What do we mean by that? So nobody knows. Nobody knew that, right? So so there's another thing another property that then comes, which is why I was careful about us falling in. And I kept saying, from our perspective, nothing happens. Yeah. So you got this Hawking radiation. is coming from the disruption of the vacuum in one picture. So it's all there, and it's coming away, and it's climbing away from this black hole. It's losing energy. And so it's very low temperature by the time you're far away from this thing. But you go in towards it then, towards the horizon. If you lowered a thermometer down from far away, so our friends are in a spacecraft now, and they've got a thermometer, and they lower it down. The idea is that it sees hotter and hotter temperatures because you're getting closer and closer to this horizon. So you've got like a fishing rod, and you're sending the thermometer down, and it's going hotter and hotter from the point of view of someone outside. From the point of view of someone falling in, there's no temperature at all. Right? You don't see anything, you don't feel anything, you don't measure any Hawking radiation. You just go in because you're in free fall. So from your perspective, nothing's happening. From the outside, you've got this high temperature. So from the outside, a description of what happens to us is different. The description of what happens to us is that we get vaporized. We never get spaghettified. As I said, the other thing is we never go in, right? So what happens to us? We get vaporized before we cross the horizon, and all our ashes and all the stuff comes out, and you could collect it, and you could say, well, that's fine, great. It's just like burning a piece of paper. But Einstein's theory is absolutely clear that from our perspective, we go in, we get spaghettified. So from our perspective, our demise, the description of our demise is spaghettification.
Yep.
From the exterior perspective, the description of our demise is incineration, right? So which one is it? So you say, well, come on, you either get incinerated or spaghettified. Which one? The modern view, at some level that is much debated, goes all the way back to work by Leonard Susskind and Gerard 't Hooft and some others. It's called black hole complementarity. And the idea is that both pictures are correct from different points of view. This is relativity in action, right? So the idea is both pictures are correct. Now, so there is it's not as simple as that. And that even is not simple because there's other stuff going on here. But so you might say, well, okay, so I understand sort of this idea that the information, essentially you're saying that from the outside, things fall in and get scrambled up and are somehow stored close to the horizon. And you can obviously imagine these bits of information coming off as the Hawking radiation. Nothing really goes in. And so it's fine. I understand how that stuff got out. But then the question is, what happens? What's the description of that from our perspective going in then? Because we definitely went in, right? So we've gone in from our point of view. What happens? What's the other description?
Are there two of us?
No, that's a great question. So you might say, well, we get copied then. So there's a copy of us, mate. It's like Leonard Susskind calls it a quantum Xerox machine, I think. So he says, is it a quantum Xerox thing? Do we get copied? So, but there's a very fundamental theorem in quantum mechanics called the no cloning theorem, which says you can't copy a quantum state. You can't copy the information. And this is fundamental. So this is a problem in quantum computing when you're trying to, it's another whole other discussion. So it's not copied. So what's the description? So this is where we get speculative and we're trying to understand what the mathematics is saying. One description of our perspective is, we go to the singularity, we get all scrambled up. And then it looks like the interior of the black hole is in some sense the same place as the exterior. You could almost picture wormholes opening up from the interior of the black hole to the exterior. And very naively, you imagine our bits of information going through the wormholes and coming out again. So we end up outside. The information ends up outside in the Hawking radiation. How it gets there, is it really wormholes that are connecting the interior? Is that what's happening? There is an idea that's been around for a long time, again, due to Susskind and others, called ER equals EPR, which is Einstein-Rosen equals Einstein-Podolsky and Rosen. Okay. So Einstein-Podolsky and Rosen, a very famous paper, was about quantum entanglement in the 30s. They wrote this paper. And they were very concerned about if you have these quantum systems that are so-called entangled systems, then you can make a measurement on this thing over here, and instantly this one, which might be a light year away, will have to reconfigure itself. The classic example is a quantum coin. So you can have a quantum coin in a quantum state, which can be heads, tails, plus tails, heads, let's say that, with a 1/√2, whatever. So if it's in that state, then it means that's a full description of the state, heads, tails, plus tails, heads. It means that if you separate these quantum coins, there could be an electron, right? You separate the quantum coins to a large distance, then it's still the case that this thing is in this, what's called a superposition of heads and tails. Then you make a measurement of it, you make an observation, whatever that you want to describe it. And if that one comes up heads, then you know this one is tails. Even though before you did anything to this, they were both in this rather, this entangled state, right? So that bothered everybody. Einstein, Podolsky, and Rosen, and they said maybe there's something else going on and whatever. But we think that's the way the world is now. Einstein-Rosen is the paper that Einstein and Rosen wrote, noticing that the Schwarzschild description of a black hole has a wormhole in it. So it's a wormhole. So Einstein-Rosen is a wormhole. EPR is quantum entanglement. So there's been this idea that they're the same picture of this. So you can picture quantum entanglement somehow.
As a wormhole between the two things?
Linking them, yeah. So this was an idea from a long time ago. And so the picture of a black hole is kind of similar to that, in that we're developing this picture where the interior of the black hole, when viewed from one perspective, is the exterior of the black hole when viewed from another perspective. And so what you're getting there, we think, and again, even as I say this, there are papers being written saying different things. It's really cutting edge stuff. But I think what everybody agrees on pretty much is that you're seeing something called the holographic principle at work here. So it's a dual description of nature. So there's a very famous paper by Maldacena called the ADS-CFT conjecture. And I think I'm right in saying it's the most cited paper in all of theoretical physics. It was a very particular model of quantum mechanics on a surface. That's what CFT, conformal field theory, it means. It's quantum mechanics on a surface. And a precise proof that there's a dual description. This quantum theory describes an interior geometry of space, which was not there in the surface theory, and the space is called an ADS space, anti de Sitter space, or whatever. But it's a proof that there's a one-to-one description between these two things, and I think it's fair to say that the black holes, these strange apparent paradoxes, are telling us that such a thing. Our universe can be described in such a way. So there are different ways of describing the same physics, and they're radically different ways. Ultimately, the thing is, it shouldn't be so problematic in that in both descriptions, the information comes out. But the way it came out is radically different depending on your point of view. And so I think most people would say we're seeing glimpses of some kind of holographic. They're called holographic, by the way, because if you think of what does it mean to have a complete description of a higher dimensional thing? So let's be very concrete. This room. So let's say that this principle is correct, and many people think it is, by the way, for this room. So we have a surface surrounding the room, the walls, let's say, and there's a theory that lives just there. And it describes fully everything that's in the room. In that sense, we're holograms. We are both holograms because we're described by a theory that lives on a hologram is a piece of film like that, and it has a perfect hologram would be a perfect 3D image, would be encoded in the surface. So it's a perfect 3D image encoded in this 2D surface. That really is the picture that we're talking about here. You can see it with the event horizon and all the information on the outside, and is the interior there and what happens. So it looks like we're flipping between descriptions of the world.
Does it feel sometimes like that story about a one-dimensional being meeting a two-dimensional being and trying to describe their circumstances, and then a two-dimensional being, and that we are somehow like seeing the weirdness of our own experience of dimensionality, and that there is, as you said, if someone were viewing us from a higher dimension, they would see this somehow clearly. And I don't really know what I'm asking.
No, I know you. It's kind of what we seem to be struggling with.
Yeah.
Is, as you said, it's almost the same struggle as a two-dimensional being trying to understand a three-dimensional world. Or actually, we do it's three-dimensional beings trying to understand the four-dimensional world, which is what relativity is. We struggle with it. It's hard for us. So this is a level of abstraction further. I think someone described the black hole as, why are we glimpsing this deeper structure of nature when we think about black holes, which are real things? And I saw someone say, it's almost as if this thing slices through space and leaves the building blocks of space dangling right at the horizon. So you can, it's this strange behavior of which gravity has created this situation where you start to come face to face with the structure of space and time. So we're talking about, as I said before, that in retrospect the hints were there with temperature and entropy and information in space, encoded in space. Why? So it looks like we're starting to glimpse a theory of the underlying structure of space and time. So this goes by the name of emergent space-time. So the picture really would be that you have a description which looks, by the way, for all the world, like a network of qubits, which is what a quantum computer is, right? So it looks like there's a description of the universe that doesn't have space and time in it, but is just a network. It's just information. And that goes all the way back to John Wheeler. We mentioned him once, the great physicist John Wheeler, who had an idea. He used to call it from bit. So it is this, and bit is information. That's what it looks like we're seeing. So our window onto this deeper theory, call it quantum gravity if you like, it has been very simple questions actually about black holes, which are real things. That very simple question from Stephen Hawking, that's why Hawking's calculation is so important, because it's the first glimpse of a problem with our picture of the world. And it's a very, very precise glimpse. So it's a precise question. Does this thing destroy information or not? If it doesn't, how does the information get out? That's a simple question. But it's led and is still leading, which is why I'm waving my hands around a lot. You would get a different pictures from any expert who does the calculations. I'm not one of those, right? But if you talk to someone who does the calculations, they would not be certain about the physical picture, I think it's fair to say.
So is it fair to say that the specific research into black holes, the specific questions that we're asking about black holes, are helping us unlock much, much deeper questions about the universe as a whole?
Exactly. It's very well put, and it's wonderful. And one of the wonderful things is that, so the techniques that you develop as let's say a PhD student or a postdoc or someone who's working in this area, the techniques that you develop to try to understand what the black hole is doing are the same techniques you need if you want to understand how quantum computers work. So, and that's a real engineering question as well as a fundamental physics question. We're trying to build these things. We haven't built one that works in the way we want to yet, but obviously Google and Microsoft and IBM and others are pouring a lot of money into it because they're profoundly powerful devices. But the insight, a lot of insight now into how they might work and how we might build them is coming from this field of emergent space-time. So it's the best example I know of, if you say to a funding agency, I want money to work on black holes. They go, Well, they fortunately they do give us some money, but they often will go, "What is it any use? I mean, what the point? You know, a black hole? Does anybody care?" The lesson is that when you study nature and you go to you try to study things that you don't understand, that pose profound questions about our understanding of physics in this case, then you are, I would say, likely to learn something useful because you're studying reality. And this is the best example of that I know, because you're studying completely collapsed stars or the things at the hearts of galaxies, and you're gaining insight into quantum computers and networks of qubits and quantum information. It's the most wonderful thing.
It's incredible.
So there's one thing I should mention for a complete picture for people who are listening or watching and want to know more. There's a thing which is really important called the firewall paradox, as it was initially introduced. And it hasn't been resolved yet. And the problem is that when you disrupt space in this way that the black hole does, and when you try to understand what's happening to the information and entangled particles that are on one side of the horizon and the other side, you know, the Hawking radiation that we discussed earlier, you do bump up against a problem, which is that maybe this description of the equivalence principle and of us freely falling across the horizon from our perspective into the interior of the black hole, maybe that doesn't quite stand up. So maybe you're getting a challenge to this basis of general relativity. Maybe it's really true that actually there isn't an interior of the black hole. And maybe it's really true that you don't go in. There isn't an in, right? And so it's you'll see if you go and search through the literature that the firewall paradox was that these papers were big papers in this debate. And then some people thought they were solved, and other people thought they weren't solved. And I think it's fair to say that the jury is still out on these issues. But what the thing to emphasize is there's something really fundamental going on here. And it almost certainly is associated with the nature of space and time themselves, or space-time. It's associated with geometries of space-time. Maybe wormholes, maybe those kind of things. So it's tremendously interesting. And you'll see, it's just wonderful to dig into this subject because it's it develops so fast, and our understanding is developing so fast. But the last thing to say is it does look like that there is a description of the universe that looks like a giant quantum computer in some sense. Cool. Which does not imply that someone built it, right? It doesn't imply that we're in a simulation. Perhaps. But it does suggest that there's a good description of reality that you can write down in the form of some kind of network of entangled qubits, which are presumably the Planck length inside. I mean, who knows? Maybe even that's not obvious, right? But something like that.
You know, I came into this story thinking that I was going to tell about falling into a black hole and then eventually get to the cutting edge of research into black holes, and that was going to be the end of the story. But actually what I'm hearing you say now is that the cutting edge of research into black holes is actually a cutting edge of research into the universe itself. Yeah. And that is just incredibly exciting. It's really beautiful, isn't it? Yeah.
They're the window, almost like the Rosetta Stones that are allowing us to translate between different pictures of the universe.
All right, so that's probably where we end.
Yeah.
If I rewind for a second, one of my questions to just connect things that I know about the universe, maybe, is what is the relationship, we think, between the singularity at the center of a black hole and the point that Big Banged?
Oh, so it's a very good question that this thing, so the singularity inside a black hole in Einstein's theory is the end of time. And in Einstein's theory alone of the evolution of the universe, there is another singularity at the other end of time, which is the Big Bang singularity, which you might be tempted to call the beginning of time. It's a very different singularity. Black holes are maximally scrambled information, right? The highest entropy things we know of in the universe. And one of the great mysteries about the origin of the universe is it's a very low entropy state. Broadly speaking, you can, if you want to know more about that, Sean Carroll actually writes a lot about this. So there's a lot of interesting stuff to say, but it's a different kind of singularity. And so are they related is the question. I would say, yeah, our understanding of them surely is. But it's really not clear. And when you add quantum mechanics in, then you begin to ask questions about whether the Big Bang, if there is such a thing as a singularity in the past, is it what is it? Is it the beginning of time? There's a thing called the no boundary idea that Hawking and others had, and again, all bets are off, right? But I think it would be good. I think not would be good. It is correct to say that I'm sure the understanding of the two is related, but we understand neither at the moment at the deepest level.
I'm sure that I am garbling fragments of understanding from things that you have explained. But does it feel related at all that there is the hologram principle, the hologram paradox that you described, that we can be described as two-dimensional, that there can be a two-dimensional kind of description of a huge amount of mass, three-dimensional mass that fell into a black hole, and that we can all... Is it possible that we are all living on the outside of a black hole right now? What is the question I am trying to ask?
I think it's a great question. I think there is a question. So there is a cosmological horizon. There are different kinds of cosmological horizons. And it is a very good question, but people don't really even know how to phrase it. But could it be that you can describe the whole universe in terms of a quantum theory living on a boundary of some description? And I think the guess is yes, the guess, but we don't even know what we mean by the boundary.
Yeah.
Right. It's one of the problems here. So the reason that Maldacena was able to show this works for this very specific thing called ADS space is because there's a boundary you can identify in that particular geometry. Whereas our universe is de sitter, right? It's not obvious what you mean by a boundary. It's not really obvious what question. As you said, it's hard to find the words. We don't really know what question we're asking. But that rough picture that there could be a theory of a quantum theory somehow, this network of qubits that gives rise to geometry, space, time, is accepted broadly, right? But when you try to get into the detail of it, it's only been fully realized for a very specific model, which is kind of a toy model. Cool. It's not our universe. So it could be that our universe does not admit that description. Could be that, but it's certainly beyond us at the moment, technically. But it's a wonderful thought. And actually there's a paper recently so people are beginning to use the Google chip, the Willow chip, which is a very powerful, it's not a quantum computer, it's a proto-quantum computer kind of thing. So, and people have started to use it because what it is a load of qubits that you can entangle and you can set it up and it's very well controlled. So whilst we don't know how to do quantum calculations on the thing, really, what you can do is try to say, well, could I set them up so that it's like space emerges from them? And there was a paper recently where something that was described in the paper as a one-dimensional wormhole was made. It wouldn't be in our universe, this thing. It would be, but it kind of emerged from this structure. And that's the kind of picture we're trying to get to. It's a good paper. It's been peer-reviewed. It's a controversial paper. You'll see loads of stuff online. But it's worth looking at those papers. And by the time this is sent out, there might be some other papers. A lot of people are working on it. So, and also actually building little clocks, little quantum clocks, little tiny clocks, and because we don't even know what a clock is, right, at the most fundamental level, because we don't know what time is. So we're talking about very fundamental questions about reality in this research, but it all came from that, right? Which is, how cool is that? It came from thinking about those things.
It's so cool. And thank you for taking that question so seriously.
It's a great question.
I appreciate it.
And I think it's really instructive that neither of us, because nobody has the language. When you get into the real detail, you're talking about mathematics ultimately. And even the mathematics is not complete. So we're talking about research at the cutting edge. And it takes a long time. I mean, even quantum mechanics, you think about quantum mechanics, if we were talking about quantum mechanics, this is a 100-year-old theory that's very well tested and very well understood. But when you try to put it into language, to speak about it, it's much easier to write down the equations or something. I mean, even Feynman says that in the Feynman lectures when he's talking about this thing called the double slit experiment. It's a great description of the way quantum mechanics behaves. But ultimately, Feynman says, mathematically, it's easy, this. I can just write down a one line which tells you how this interference works and all those things. But then if you try to say, well, what does it mean? What happens? What does it mean for our picture of reality? Then we're still arguing about that now. But the maths is easy. This is even worse because here the maths is really difficult and we have no idea what it's telling us really about reality.
One of the things that I really admire about you and your work is that you have this sense of wonder at the universe. And I think that the thing I've most appreciated about it, and I'm sure I speak for a lot of people, is that you give that sense of wonder back to people. You say, hey, don't you remember what it was like when you were a little kid looking up at the sky? And actually, in fact, as you learn more about the universe, that sense of wonder can increase, not decrease.
Yeah.
And I think that's really special. And I think that people need that. And first, I just wanted to say thank you.
Oh, thank you.
And second, my last question for you is, how do you feel when you go outside and look up at the night sky, given what you know?
Oh, it's a wonderful question. And you kind of alluded to it earlier, that the sense of awe and the sense of mystery and beauty increases the more you know about what you're looking at. It doesn't decrease. The mysteries, the number of mysteries increases the more you look at it. And it is incomprehensible, even if you think about the Milky Way. So it's a beautiful thing to look at. So anybody watching this, if it's a clear night and you're away from the city lights, you can go, we've all looked at the Milky Way at some point. If even that, if you try and picture what it is, and you learn that it's a galaxy of, 200 billion, maybe 400 billion suns. What does that mean? 200 billion suns. Most of them have planets, so it'll be trillions of planets. It takes light 100,000 years to cross that thing. None of that is I think, you can't internalize even that. And that's kind of a simple thing, because it's just a galaxy, and we know about galaxies. And then you talk about, as we've talked about, the center of that galaxy lies this thing, the supermassive black hole. And then we don't know. We don't know what that thing is. You can look towards it. So you can look towards Sagittarius. The further south you are, the easier it'll be to look at. But you can look in the direction of the center of the galaxy. So you can go out, if you're not too far north, and look at that. Right? You can look at it with your eyes and and wonder about it. So that's what I really believe. I know Richard Feynman said it many years ago, and many other people have said it, but the more you understand about nature, the more mysterious and magical it becomes.
It's a beautiful place to end. Thank you so much for your time.